Okay, so hybrid simulations. So in the hybrid simulations, I suppose that I have a source here that emits a random Brownian particle at steady state. Brownian particle at steady state. That is, you wait, no fluctuation in time. Great. And so then, suppose you have your cell, and I have an abstract domain, and here I have the receptors. So, what is this? So we know that the solution of the number of receptors in the domains is, this is a solution of, so you remember dp/dt, the probability density function, is solution of the Fokker-Planck equation, which is the classical diffusion. That's what we did last time, and if it's, you put all the source at position x, let's say at time 0, you have n particles, you have a delta Dirac at this position, and on the source, you can tell that no particle can penetrate, so this is called reflecting boundary condition. So nothing can go in here, reflecting except at the receptor where you have absorbing at the location of receptors, which means this and this. There are two positions. And at steady state, you can integrate this from 0 to infinity. And yeah, so this is associated to what is called a Green's function. So this is, so if I integrate, okay, I'll do slowly. I call gx x0, the integration from 0 to infinity of px x0 of t dt. And if you integrate this, you know, you can integrate this, which means integrating a derivative is the same. So this is p at infinity, which is 0, minus p at 0 and x, which is a delta Dirac, equals d Laplacian j. So this is 0, and this is by definition here, this is the Dirac. So you get minus delta n d Laplacian j. And so what you want to calculate from this is the flux. And the flux are the Ji. The flux is the integral of, this is what you learn in elementary university years. It's dg dn, this is the flux. You have to integrate over all of the sides here, let's call it d omega I, with a minus ds. And that's the flux. This is the number of particles per unit of time. Number of particles per unit of time, arriving to receptor I. Okay. Okay, so suppose you know this. That's what you want to calculate. Now I want to replace this. You remember what we said? I want to replace this. So this, all of this. I wish I knew how to calculate this. Maybe it's very hard, and we will do this in the second part. I want to replace this by, this has to be replaced by, you start at the source, this is the cell. I want to ask what is the distribution of a molecule if it starts here on this. Obviously, if it's closer, you have more probability that it's further away that is behind. So what does it mean? It means that I want to replace this. Now you have to think about the probability. I said, all right, up to here, when a particle arrives here, then it will be absorbing this disk. So how shall I modify this equation? So we say that, all right, you start with the same equation, with Laplacian J equals minus n delta. We don't care about this because I'm interested in ultimately the probability, that doesn't matter. And if here the molecule will be absorbed, I'm going to add J equals 0. This is absorption. This is the same as I did it here, but except now I do it further away. J equals 0 on the imaginary disk, which is this one. It is R. For example, I fix this 2R or 3R, whatever. You design it for your simulation. So, what do you need to calculate? Well, you need to calculate here. This is the flux. This is total flux. If I knew one receptor. So now what I need to calculate is the total flux here, which will give me the probability if I divide. So what's the probability to be located here? What is the probability? What is the probability to be located at this position? Let's call it, I don't know. I can define, for example, if I'm in dimension 2, I say this is an angle theta to be located between theta and theta plus the little thing, like an elementary element. What's the probability? Well, this is what I described to you. Let's look at the flux here divided by the flux everywhere. And the ratio gives you the probability. So that's exactly what you need to calculate. The probability to be located at time theta condition that you started at S is going to be the flux dj dn divided by dj dn integrated over your abstract disk. Let's call it imaginary disk of radius r prime. That's this guy. This is the imaginary disk. And that's the probability to start here. That's beautiful. It means that if I know that you started here, I know what's the probability to start at this position. I know the probability to start at this position. I just have to calculate this quantity if I know how to solve this equation. And I know how to solve this equation. I'm not going to do the exact, to show you how to calculate. It's well known. I mean, well, okay. Just back up a second. Do you know what is this equation? This is what that you've learned for high school. This is Laplacian J, the Green's function. It's called J, is a function that we're looking for. Equals delta Dirac. That's exactly the same in electrostatic. When you have a charge, you put the charge at a point and you calculate the voltage generated by one charge. That's exactly what you have studied at school. So except that if you're in dimension 2, so you know this is called Coulomb's law. Have you ever heard of Coulomb's law? If you have a charge, it's N, or if you have Q, your charge Q is Q divided by R, and this is the potential. And then it leads to 1 over R, where this is the distance between the source and the position. You remember this? This is elementary school. That's the solution of this equation. Now, if you have boundary condition, it's a little bit more complicated. And this is for dimension 3. This is what Newton's found for gravitation when you have a mass. That's the classical Newton's equation. Now it's a little bit more complicated. I want to impose 0 boundary conditions. I'm in dimension 2, so this is not going to be exactly, this is going to be the same in dimension 3 when we do the simulation in dimension 3. So in dimension 2, I'll give you the results, and if you're interested, you can go to our publication. Now, this is just to tell you that the equation I'm treating are not very hard. They belong to the background of any scientific student, So the solution is, when you start at position x, x is the source, and you end up at position y, it's minus 2 pi, so I suppose n here equals 1, because I don't care, n and n will drop, because I do the, if I have an n somewhere here, n it will go away. So minus 2 pi log of x minus y minus log of x minus r squared divided by y squared, y minus log of y divided by r. R is the size, I should call it r prime. R prime. And the 2 pi is in front of everything. Okay, and 0 here is this center. That is, when I say x, x is with respect to this frame, where you start at 0. So 0 is the center of our reference. That's great. Now I have to differentiate this. You know how to differentiate with respect to a normal? dj dn is the gradient of j, gradient of the function, multiplied by the normal. The normal is the vector, little vector, that points out to your domain. Okay, it's not very, that's the meaning of this notation. Gradient, you know what is the gradient of the function, right? It's a derivative with respect to the direction. Okay. So that's beautiful, because, so I'll show you, I will write the calculation. P is probability of theta. So probability that suppose, so this is, you start with an angle theta prime with a radius r. Yeah, let's call it, because I have many r, let's call it a. So P is equals to so r will be here the magnitude of x, rho will be the magnitude of y, and r is the ball. So you get 1 over 2 pi r squared divided by r squared minus this, and you have r squared divided by r squared minus 2r capital R cosine theta minus theta prime plus 1. Whatever, and this is r squared divided by r capital R squared, so this is r prime, r prime, r prime, and this is pi. But this is a probability if you start at a certain distance away at position x, which is r theta prime, you end up in here, which means that, how do you generate your trajectory? You start here. You take your random generator, go to your computer. You draw a probability according to this distribution. If it was a constant, it would be a uniform distribution, but it's not constant, so it has to be modulated according to this. You start here. You don't generate whatever happened outside. Now you generate your Brownian simulation. It finds the point, you stop. It doesn't, you wait. If it exits, you see where it exits, and then you repeat. Now you have exited here. I can repeat, this point is the same as that one. I can repeat all the procedure according to that point. And I start afresh. And that's the algorithm. Alright, so that's the way we design this algorithm, and it works. What I call here, this is a very important function in mathematics if you are interested in simulations. It's called the Green's function. This is called Green's function. It's very important in mathematics. Green's function. If you have ever heard of this. When you solve this equation here, of this type, with Laplacian and Dirac, this is called Green's function, which captures the information about the geometry. Okay, so this we have been, and now it means that you are capable of making simulations. So each time that you have to do a Brownian simulation, you can ask yourself, maybe I don't need to generate hundreds of thousands of trajectories. You remember the class we did last week or the week after about extreme statistics? In extreme statistics, you have to look at the rival of the fastest. The guy that will go, I gave you the example of the marathon. In marathon, you look at all of these people and you're interested in the first one to arrive. Signaling by extreme statistics is signaling by the first ion that will arrive to one specific place. So we had the work on this, we haven't published it yet, is I don't need to simulate hundreds of thousands of trajectories. Maybe I can simulate in a clever way the statistics of the fastest if I know how to solve some equation. So then you can ask yourself, maybe what I'm showing to you here can be true in many occasions when you have to simulate random events and you need to accelerate the procedure. Okay, I think I'm not going to hit too much of your time. Maybe I'll postpone it for next week. Next week, we will do the triangulation problem. Next week is next Thursday, and next Thursday is okay. Yes. So I'll stop here. So what we are going to study next week is so it's going to be close to what we're doing here. Suppose you have 3 receptors. And suppose J, the flux is known. But the flux depends on the initial position. That's why I explained to you. So it depends on the position delta Dirac at position x0. So J of x depends on x0. So suppose I give you J1 of x0, J2 of x0, J3 of x0, and so on. Jn of x0. So I have a matrix. From this matrix, so that's what you... Can I invert the matrix with respect to x0? In other words, can I find x0 as a function of J1, Jn? And if I know how to do this in a unique solution, I'm good. I will find the position according to the flux. So I need to do an inverse type problem. And you will see, I explained to you, this is how we found new coordinates. Because this can correspond to coordinates. You know, if I have x, y, and z, those are coordinates, you agree, in a space. It's coordinates. I'll explain that this can also be seen as coordinates. This, after the class, after we go to the calculation and explain, we invented, and we have a review 2022, but maybe those are interesting coordinates. So the review is Dobramysl, myself, and this is report, progress physics, where we explain that this is actually doable, and and that's what we're going to see next week. Okay, so I give you a lot of information today, a lot, about how neurons move, what's the importance of the gradient, how you can simulate cell motion, how you can account for attraction, repulsion. I didn't go into the mathematical details, a little bit, but not too much. We discuss the complexity, and I haven't shown, but there's a combinatorics. You know, if you have many gradients, how you choose the right one. Then we discuss, finally, if you are interested from a computational point of view, from a computer science point of view, how do you simulate? If you simulate all of this, it's heavy, it's hard. So the best way is to remove the complexity, or remove, let's say, the amount of simulation by, when you can, doing hybrid simulations. So this is a concept that people in Wikipedia liked. They had, if you look at hybrid simulators, stochastic hybrid simulation. They also summarize it in Wikipedia, where they use our scheme, and there are other schemes, so that it can be useful. Of course, what is the limitation? If you are not at steady state, it's very hard. We don't know how to generalize this. Okay, so next week we'll finish this. Maybe we move a little bit on with some signal processing, and then we'll be ready for the second part of the class about neuronal network, glial network, brain, how the brain is, how we want to model and understand and do data analysis for neuronal networks and glial networks, so that we can go to complex brain functions. So we leave the brain development for the field of neuroscience.